Welcome back, students. This is the video for practice set 4 in ABI. And let's go ahead and just jump right into it. We'll start off with number 1. Below is the table DT. Write the code for the correct categorical column. All right. So here we have a table, and I have to basically look through the columns and see what's the categorical column. Now, right off the bat, I have one character that's population density. It's going to have high, medium. Here I just say high, medium, but let's assume it's high, medium, low. The other thing else looks like it's actually integers and numbers. So for number 1, I'm just going to write the factor function for this table, and it's just going to be on population density. Now look, I have actual words, high, medium, low. So it's a character. So remember, and the next question I ask you is, look, is this a nominal categorical data, or is it an ordinal categorical data, right? So the question is, does it have magnitude or doesn't it, right? And of course, there is magnitude. Low, medium is larger than low, and high is greater than medium, okay? So it's going to be ordinal, and now this ordinal, there's going to be an extra level of complexity because it's a character, meaning there's words, and it's ordinal. So when I declare it as ordinal, I must also, it's important that I also have the levels in the order that I want it, from least to greatest. So I'm going to type it up in R right here, and then copy and paste it into Excel, just so I don't make any mistakes, because I think sometimes I make coding mistakes when I'm doing it straight in the Excel. So the name of the table is DT, comma, and the name of the column is pop underscore density equals factor. All right, and I want to factor on pop underscore density. Scroll this over a little bit so I have more room. Okay, I'm going to have levels, and the levels will be, right, notice that I will have to pass that into the C function again because I have multiple levels. But the levels are what? High, medium, low. Now, remember, case matters. Case matters. You cannot put lowercase h, medium, and low. It's gonna. You guys have some of you guys have seen this. If you do that, all of a sudden there's no values in that column, because that column is only allowing the values capital H high, capital M medium, capital L low. So case matters. So here, I will make sure I have the right cases: low, medium, and high. All right, and I have to do the levels explicitly because I'm saying ordered equals true. All right, and that's the one answer for that question. Copy it over here so you guys have it. All right, there it is. Number 2. Which data, let me slightly make this, scoot this over a little bit. All right. Which data is the closest to being, or which set of data is closest to being normally distributed? Okay, now, who remembers what's the trick when you're looking at the range of data or the summary of data, how you can tell if something is similar to being normally distributed? That's right. You look at the mean and median, if they're exactly alike, that's saying, hey, this is perfectly normally distributed. And why is that? That's right, because the mean is highly sensitive to the outliers, whereas the median is not, right? So in this scenario, I think next time I would give you like more differences between the median and mean if I ask a question like this. So here I have a 0.01 difference. Here I have like another difference by decimal places. Here I have a difference by 0.15, and here I have a very, very large difference. So that's out of the park. The one that's basically the closest between them is this one, A, right here. But rest assured, in an exam, I'll make a more extreme example, so that's easier to see. All right, number 3. Oh, here I got a little ripped off a little bit, but okay. So which graph would you use to visualize between the numerical and categorical data? Yes, people. What graph would you use if you want to compare if you want to visually compare the relationship between a numerical and categorical data? And the answer is box plots, right? Box plots. Good old box plots, right? You're going to put what's going to go on the x-axis? Your categorical data will go on the data on x-axis, and your numerical data will go on the y-axis. All right. That's a little bigger. So hold on, let me save this file. Save as, just so I don't lose that. Documents. All right, there you go. All right. Number 4, using the graph below, how many math majors are there? All right, this is basically, guys, this is from, God, I want to say geometry. I mean, it is from stats too. Fine, it's from undergrad stats. We can go far as that, but there's nothing like rocket science here. So using the graph below, how many math majors are there? All right, so the math is blue. So I have 3 math majors that are juniors. I have 1 that's a sophomore. So I have basically 4. I have 4 math majors. Number 5. Using the graph below, how many sophomores are biology majors? All right, how many sophomores are biology majors? So here, again, biology is now red. So here's the sophomores right here. Notice, by the way, this is out of order because when I made this graph, I probably didn't properly categorize this as a categorical data. So this is why I went to alphabetical instead of actual categorical data. But anyway, so how many sophomores are biology majors? Here's the sophomores. There's total 3 majors and sophomores, but only 1 to 2 are actually biology majors. The answer is 2. And that's easy. All right, number 6. Using the graph number 5 and table below, graph number 5, this one, and the table below, how would you show the same graph split by sex? How would you show the same graph, this one, split by sex? All right, so what am I getting at? What am I getting at? Facet underscore wrap. Remember when we did that? Facet underscore wrap. So here you would have 2 graphs side by side, one for the males, one for the females. And so how would we do that? Well, using this table, we would simply do, it's a bar graph, that's number 1. So it's going to be ggplot. The name of the table, I did not give the name of the table. So let's assume it's just dt. dt AES. The x-axis goes your what? Your year, the year that the student belongs in. On the y-axis, right, there will not be a y-axis because it's just going to count up those values. But we are going to have a fill based on the major, right? We are going to have a fill right here based on the major. So here we're going to put in major. Close that up. Now I want this to be a bar graph. All right, it's going to be a bar graph. And I don't need to put anything else besides that it's a bar graph. Now this graph right here, this statement right here will give me that bar graph using this table. Okay? Now if I want the split side by sex, right, show the same graph split by sex side by side, I'm going to go ahead and do tilde, because I'll do it side by side, and sex. It's that easy. All right. Number 7. What is the correlation of the below graph? All right, look at this. You got a horizontal line going straight across. You got a cloud of dots that show no clear pattern. So what's the correlation here, guys? Remember, a positive correlation means a positive number. A negative correlation means a positive correlation means the line is A diagonal line sliding upward. A negative correlation means a line sliding downward. A line going completely horizontal is 0. What are the values of correlation? They're from 1 to negative 1. 1 to negative 1. 1 meaning perfect positive correlation. Negative 1 means perfect negative correlation. And 0 obviously means no correlation. So what is the correlation here? It's perfectly 0. Look at that. All right, easy peasy. Number 8. All right, which line assumption is violated if the scatter plot of the independent and dependent variables have a curved line? The independent and dependent variables have a curved line. All right, first of all, when we graph the independent and dependent variables, which are both numeric on a graph, what are we getting? We're getting a scatter plot, right? And if that scatter plot has a curved line, tends to have a curved line or curved pattern, which one is being violated? Linearity. Linearity. All right. Number 9, which line assumption is violated if the histogram of the residuals are skewed to the side? The histogram of the residuals are skewed to the side, one side or the other, right? That is attacking normality. Remember, we use 2 graphs to look at normality. That is one of them. Which line assumption is violated if the scatter plot of the residuals and residual z-scores are curved to the side? All right, if the scatter plot of the residuals and the residual z-scores are curved to the sides, right? Or they're curved to the side, so it's not a straight diagonal line. That is the QQ plot, right? That is also violating normality. Number 11, which line assumption is violated if the scatter plot of the residuals and the predicted values show a pattern? All right, if the scatter plot of the residuals and the predicted values show a pattern, that is equal variance. Right, a linear regression model predicting the linear effects of the amount of water used in growing almonds is developed below. All right, so here is the linear regression model we saw for. The water data when we're making the model, right? When we're making the model, has a range of data from 5 to 90 and is in units of 100 gallons. Okay, so basically 500 gallons to 9,000 gallons. All right, 500 gallons to 9,000 gallons in actuality, in business speak. But the data is just 5 to 90 in units of 100 gallons. And the almond data is just purely in pounds. According to the model, how much pounds of almonds will grow if no water is used? Okay. Now, first of all, what is my independent data here? My independent data is the gallons of water. What is my dependent data? It's the pounds of almonds. Okay. Now, according to the model, the question is how much pounds of almonds will grow if there's no water used? If no water is used, x becomes 0, and then we have the answer 56, right? And that answer 56 is in terms of pounds. It's in terms of pounds. So the answer is 56 pounds. 56 pounds of almonds will grow if you use no water. Okay? Of course, that doesn't logically make sense, but that's basically what the model is inferring from the data. Using question number 12, how many acres will grow? Oh, sorry, this is a typo. This should be pounds. How many pounds will grow if 1,000 gallons is used? Okay, how many pounds will grow if 1,000 gallons is used? Okay, first thing we do is we take that amount, 1,000 gallons, and we convert it into the numeric amounts, into the numeric scale that our model was trained on. So because all the units over here are basically in terms of 100 gallons, right? I'm basically going to take this and divide it by 100 gallons, and I'm going to get the number 10. I'm going to get the number 10. I take that number 10, and I plug it into my model. So it becomes 10 times 10, which is 100. 100 plus 56 is 156, right? Is 156. Oh, sorry, for number 12, I didn't put the answer down. Answer is 56 pounds. I put down 56 pounds. And number 13. All right, number 13. So how many pounds, this is a typo again, how many pounds will grow if there's 1,000 gallons used? 10 by 10, 156 pounds. It's going to be 156 pounds. Right? Question number 12. How many pounds, again another typo, will grow if I used 400 gallons? If 400 gallons was used. So again, I divide 400 by 100. I get the number 4. Some of you will take that number 4, multiply by 10, and get the answer 96, and put down 96 pounds. And those that did that would be wrong. Would be wrong. Why? I divide this by 100, and I get the number 4. Okay? But when I come over here and I say I want to plot 4 in here, can I plot 4 in here for this model? I cannot. Because this model was made from the range 5 to 90. 5 to 90. Therefore, we talked about this last week. Therefore, I cannot use it. I cannot use it to predict how many pounds of almonds will be grown if I use 400 gallons of water. It's beyond the scope of the model. It's beyond the scope of the model. Therefore, the answer is the model, we could just basically say beyond the scope of the model. Or you can say the model's not trained to answer that question, right? Beyond the scope of the model, or the model's not trained or created to answer that question, right? That's a trick question. It shouldn't be a trick question, but you know, the first time you see it, it's kind of weird. Using question number 12, an increase of 100 gallons increases almond production by how many pounds? Ah, yes. An increase of 100 gallons is basically an increase in my X input by 1, all right? By 1. Because remember, it's in gallons, the unit is 100 gallons. So by 1 would increase this, how many the pounds by how much? It would increase it by 1 pound. So 100 gallons, an increase in 100 gallons of water, it gives me 1 pound, 1 additional pound of almonds. By the way, fun fact about almonds. Obviously, me being from the Middle Eastern Asian world, we love our almonds, right? But almonds have especially in California, they take tremendous amount of water to grow. So a lot of people don't know that. They take tremendous amount of water to grow. And so a lot of times when California was having water shortages, there was a lot of complaints because the almond farmers in California were still getting tons and tons of water to grow those almonds. So fun fact about almonds, very inefficient in terms of water usage. Number 16, a linear regression model predicting the linear effects of the amount of water used in growing the almonds is developed below. Again, same thing as before. Now I'm getting a little fancy on you. The water coefficient, right? The water coefficient has a t-statistic of 5.7 with a p-value of 0.002. All right, a t-statistic, or basically the t-value, right? With a p-value of 0.002. Do you reject the null hypothesis for the water variable? All right. What the heck are we saying here? First of all, I give you the t-statistic or the p-value, and I haven't given you a couple things. I haven't given you, the coefficient you have is 10, but I haven't given you a standard error, but that's okay. You could back that out, right? Remember, you guys remember the formula, right? It's basically the coefficient value divided by the standard error. That's fine, right? But More importantly, we have the p-value here, and we did talk about the p-value. The p-value basically tells us how far, what's the probability of that value, what's the probability of getting a t-value of this magnitude that is greater than equal to this value, right? If the mean of this distribution function is 0. Remember, t is always going to be 0. T is always going to be 0. That's the mean. T is 0. Okay? And what is the null hypothesis? All right? So just as a refresher, when you're doing linear regression, remember, when you're doing linear regression, all the values that come back from those coefficients, basically, in this case, my how many gallons of water I use to grow almonds, the assumption is, remember, we're skeptical. We're scientists. We're always skeptical. We're saying, hey, the value we got back was 10. That was the coefficient, 10. But we're skeptical if that is not just a random error of some sorts. In other words, our null hypothesis is basically saying that beta, I'll say beta 1 here, equals 0, meaning beta 1 is what? Beta 1 is regression speak for the first coefficient, is the first coefficient value, 10. That in actuality, the true value, this is just some random error from the sampling of the data we had, but in actuality, the true value is 0, meaning that in actuality, the amount of water you use has 0 linear relationship to the amount of pounds of almonds you grow, right? And the alternative is, I'm sorry here, I don't know how I can get the not equal thing here. I'm sure I can pull it in, but basically, I'm going to just say not equal to 0. But you guys know what it's basically the equals with the slash and all that other stuff, right? So not equal to 0, right? The equal with the slash in it. That's the alternative. So this is the null. Let me just move this over here. This is the null hypothesis, and this is the alternative. Okay? So we go into, every time we do a regression model, we go into it saying, hey, the result we got back is rubbish. There really is no relationship, right? And that's why we look at the t-statistic. And the t-statistic, remember, again, is the coefficient value, 10 in this case, divided by a standard error. Now, when the standard error is large, remember, because standard error is in the denominator. You guys know your basic mathematics. The larger the denominator, the smaller that fraction, okay? What does that mean in terms of normal data speak? What that means is, or analytics, what does that mean in terms of normal analytics that we're talking about? So what that means is the number we're calculating, we're measuring, or we're predicting, this 10, right? If the errors around it, if the standard deviations in basically calculating this 10 is so large, then we can't really put that much faith in that number 10, right? And that's what the t-value or the t-statistic is showing. It's showing the t-value is the coefficient, the calculated coefficient value, which is 10, divided by the standard error around calculating it, right? So, for example, let's say the standard error was 10. 10 divided by 10 gives you 1. That's not a really big t-statistic. That's close around 0, right? That's close around 0. If that's close around 0, then from the point of view of the regression model, it's not, that value 10 is not statistically significant, and therefore we fail to reject the null hypothesis. We don't see any data that tells us, hey, you should take this value seriously. That's what we fail to reject the null hypothesis. Know what I'm saying, by the way. I'm saying we fail to reject the null hypothesis in that situation. Not that we accept the null hypothesis. As scientists, we never accept a fact. We just fail to reject that fact until we can. That's basically it's a philosophical point of view from science, right? If you want to think about the way science, the hypothesis theory and the scientific method works, we never prove things per se. We just fail to reject. A certain hypothesis, right? We just fail to reject a certain hypothesis, and we save it for another day. Another day we can reject it. Today we can reject it. So it's a little subtlety in the world of regression, but that's the way it basically works, right? So come back to this now. This example, t-statistic is 5.7. That seems like a large number, right? We know it's a large number. Why? Because if I were to use R and get the actual critical regions the critical regions of the regression. Now here, first, I think it behooves me, yes, I use the word behooves, to show you what visually, if I can find it, hold on. I'm going to attempt to draw you what I am talking about. Where are we? Okay, excellent. PowerPoint. PowerPoint. All right, bring this over here. You guys can see what I'm talking about. Get rid of that. All right. Now what I want to do is show you what I'm talking about. So insert, and I want to do no shapes. All right, yeah, I'll do this. Right here, I'm going to grab some freestyle, scribble. So here we go. This is a horribly drawn normal distribution. Again, I apologize. I'm not an artiste like some of you. Stop laughing at me. All right, so let's assume that's a perfectly drawn normal distribution, right? Again, the distribution you guys have seen forever and ever and ever. It's the most popular distribution used because one, it's so elegant and so easy to use. Two, a lot of things in natural and scientific and physical sciences do actually follow normal distribution. It's very like supernatural, if you will. All right, so here, let's say this is the center line right here. Okay, and here, guys, t equals, assume that's a lowercase t. I don't know why. Stop it. All right, t equals 0. Can everybody see that? Let me make the font bigger. Make the font. Boom. Now you can see that. All right, t equals 0. See that? T equals 0. I should also put a line underneath it. Hold on. All right. Right, and remember, the normal distribution is what we call a continuous distribution because the tails just keep going out till infinity. All right, they keep going out till infinity. Scoot that over a little bit. All right, cool. All right, so that's t equals 0. As I was saying, all right, I'm now going to grab this. When we take a sample of data, right, we get a range of answers, right? We get a range of answers. We talked about the confidence interval, right? The confidence interval basically says, hey, we're 95%, 90% confidence, or 95% confidence, or 99% confident that the value we got, in this case, the coefficient we got, will be within a range of numbers, that the value we got, basically the range of values we got, right? Because within the coefficient, you can actually calculate a 95%, 99% range. And that range, basically, we're saying that range will encompass the true coefficient value from the population. I don't know why I can't put a straight line here, but it's supposed to be a straight vertical line here, right? And here. So now why am I drawing two critical regions? Because unlike the F test, the T test has two critical regions because it's a normal distribution, right? So the T can be around the mean. But if it gets too far around the mean, the T value, well, there's a slight problem there now, right? So if it gets too small here and too large here, past the critical regions that are designated based on how confident we want to be based on our interval, our confidence interval, right? Be it 90%, 95%, and 99%. And again, the confidence interval, all the confidence interval is saying when we say 90% confidence, we are saying that 95 times out of 100, our range of values under our T over here will be indicative of the T population. But 5 times out of 100, that T population number will be outside the range. That's what confidence interval means. Confidence interval, it's all about the interplay between a sample of data versus the population data. And if you remember, I did that experiment for you guys in our slides last week where I took a sample of the marketing data at 30% of it, and I tried to figure out what the actual coefficient value was of the whole data, right? That is the thought, basically, the thought experiment of what statistics really is, what's happening there in statistics. Sampling against a whole big set of data. All right? So if the t-value is here, that t-value is way too small. If the t-value is here, that t-value is way too big. That signifies what? That signifies a situation, and again, the reason why you can get a negative t-value is because your coefficient could be negative, guys. That's all that's basically happening. Remember, your coefficients can be positive or negative. It need not be a positive coefficient. It could be a negative coefficient. Absolutely, right? The coefficient, your independent variable, could have a negative linear relationship to the dependent value. It doesn't need to have a positive one. Okay? So what that is saying in both scenarios is that standard of error is way low. That standard of error is way low, right? So if that standard error is way low, how do I get a coefficient value? Now we go back to here. How do I get a coefficient value of 10? Right? How do I get a coefficient value of 10? Well, that only can mean that the independent coefficient truly does have some sort of linear relationship to the dependent variable. Because there's something else besides random error causing that t-value to be so away from the zero mark here, right? And so when the t-value is beyond these critical regions that are, again, designated by whether we want to be 95% confident, 99% confident, 90% confident. By the way, the default tends to be always 95% confident, right? So this area right here, remember, this is a normal distribution. The area around the normal distribution is 100%. This point this way, this critical region from this point here, this area is basically, this area is for a 95% confidence interval, this area is 2.5%. Let me make this bigger. Boom. Okay, 2.5%. Copy this. Slide that over here. This part over here, this region, again, this is for a 95% confidence interval analysis. This region here is also 2.5%, meaning that from this point to this point, the probability under the curve is 95%. Okay, it's 95%. Now, when the t-value is here, right, its p-value, probability value, right, it's going to be 2.5% or less. 2.5, remember, this point right here is 2.5%, this point right here is 2.5%. Now, over here, that look, we got this coefficient, 10 right here. Its t-statistics was 5.7. All right? Where do you place that 5.7 here in this graph? You don't know until it tells you, hey, the p-value of that 5.7 is a positive number, 0.000002. It's virtually zero, meaning it's not here where the area from this point onward would be, again, this point here onward would be 2.5%. It's somewhere out here. It's somewhere out here, way behind the t equals 0. What that implies is, hey, that coefficient is not driven purely by random error. There's something else driving that value that we got 10. Therefore, we are going to reject the null hypothesis that beta 1 equals 0, or basically that coefficient 10 is 0. And we're going to accept the alternative that 10 is truly not 0, meaning that coefficient, the 100 gallons of water, right, in units of water, the gallons of water, does in fact have some sort of linear relationship to the pounds of almonds being grown. All right, to the pounds being grown. And again, if you wanted to find out what the actual values here in the t-value, we have our function for that. In R, if I type in QT, again, this is a 95% confidence interval, 0.95, and then I put the degrees of freedom in, Again, what's the degrees of freedom? Well, in this question, I don't tell you, because to get the degrees of freedom, you have to know how many rows of data you're using to train the model. In the next question, I tell you 200 rows of data. So let's just assume for number 16, it's 200 rows of data as well. And so what's the formula for degrees of freedom once you have for linear regression? It is, when you're doing a t-statistic, it is n minus p minus 1. N, the number of rows you have. Let's assume, again, it's 200 rows of data. Minus p, that means predictors, which that basically means the number of independent variables you have. We just have one independent variable. So that's going to be n minus 1. That's going to be 200 minus 1. And then minus 1 just for the intercept. So that becomes 200 minus 2. 200 minus 2, which is 198. So if I stick in 198 here for degrees of freedom, I get 1.65. What that means is the critical region here for t starts at, oh, let me just copy and paste this bad boy. (1.65) negative 1.65. All right, and that's the negative region, right? So it's negative. So anything, and then right off the bat, you don't know. So anything basically at any t-value that has a t-value greater than 1.65, you're in the critical, you're in the reject and null hypothesis region, or less than negative 1.65, you're in the reject. You're also in the reject of the null hypothesis region. Okay, so that's why here, finally, I went the long way around, but I wanted to stress this point because, again, even though this is a review, right, linear regression, for some of you people, I guess this is the first time you're actually looking into what's going on here with regression and these values. So here we end up rejecting the null hypothesis. So the answer is we reject the null hypothesis. All right, number 17. Number 17. So number 17 now, we have a linear regression model predicting the linear effects of the amount of water and the amount of sunlight used in growing almonds developed below. Okay, so here, guys, I do have a typo. I apologize. I have a typo here. There should be an additional variable, which I'm missing for some reason, right? So it should be y equals 50, y equals, so let me put it right here. Let me write it right here in the answer sheet. Okay, so this is going to be y equals 56 plus, actually, right, typo. And it should be y equals 56 plus 10x plus, let's do 5. This should actually be a subscript, 10x1. I can't do a subscript here, so I'll do 10x1 plus, let's do 2. Let's do 2. 2x2. All right. So now here we have a multi-regression model. Now here, again, the data has 200 rows of data. The water coefficient has a t-statistic of 5.7 with a p-value of 0.002, just like we did above. The sunlight coefficient has a t-statistic of 12.6 with a p-value of 0.68. Okay, with a p-value of 0.68. Now, yeah, this number seems a little out there for me right here, because that 12.6 number doesn't really jive usually with the 0.68 number, but let's just go with it, right? The focus here is on the p-value 0.68, right? For the exam, I'll have a number that's more coherent between what the t-statistic should be and then what the p-value should be, right? But focus on the p-value being 0.68, right? Focus on the value being 0.68. The model has an f-statistic of 5. Now, do you reject the null hypothesis for the model? Okay, that's why I asked the question, right? Because that's a red herring. Do you reject, the model has an f-statistic of 5. Do you reject the null hypothesis hypothesis for the model. Not a particular variable, just for the overall model. Just for the overall model. Now, remember, the F statistic now, it does a null hypothesis test on the whole model. And what is the null hypothesis again? Here it's basically, the null is going to be beta 1 equals beta 2 equals 0. All the coefficients are 0. That's what the null hypothesis is saying, that all the true value of the hypothesis of the coefficients are all 0. Not this whole model, none of the coefficients in this model has any linear relationship to the dependent variable. Okay? Therefore, the alternative is what? The alternative is that at least one, and I'm sorry I'm not writing this in mathematics, but this is what it's basically saying. At least one coefficient is not equal to 0. Not all, just at least one. If we had a linear regression model, multilinear regression model with 20 independent variables, right? With 20 independent variables, the null hypothesis would say all 20 independent variables are equal to 0. The alternative would say that at least one isn't. One out, let's say 19 were, but one wasn't, then we would reject the null hypothesis because all of them are not. All of them are not truly 0. All right, all of them not are truly 0. So now, if we're at this point right here, right, let's go ahead and do this. Now here, I said the F statistic is 5. I give you the rows of data. I expect you to do more work here, right? And what's the more work I expect you to do? I expect you to use, well, in the exam, I'm going to give you a table. I don't give you the table here. I'll literally give you a table so you can figure out what the F, you have to figure out what the F critical region is and all that jazz. But here we'll just do it in R, right? And just as a refresher, right? Let me do another beautiful image for you guys. Let me do a new slide, blank, right? Let me insert right here. Oops, what's going on here? Stop. I need a new trackpad. So insert. All right. So now I will do down here. All right. And I will do another insert of a line here. Look at that. All right, look at that. Let me make the lines a little bit solid. I should have made the lines more solid in the other one. I don't know if you could saw that, but so here, I'll make this sucker heavier. Boom. Right? All right, now I'm gonna do my little freestyle drawing. Now, unlike the T distribution, the F distribution is one-sided. It's simply one-sided. Let me go my scribble, and it looks something like this. Boom. Oh, it's gonna be bad. Oh, like this. It's a one-sided test, like this. Oh God, I gotta do that again. Let me do that again. All right, so it's going to be insert. All right, start off here. All right, so something like this, right? It's a one-sided test, okay? And what happens here is just like before, and this graph, this graph should be going out further. So it should be going out like that, further, whatever, right? Oops. All right. So now what happens is we set up a critical region in just one side, right? And again, I have a better graph in my notes, right? It's a one-sided test. It should be like this, and it tails off like this. Here, this side is a critical region. This side So basically, if any f value that goes here, basically we reject the null hypothesis. Any f over here, we fail to reject the null hypothesis. All right. So the question is, what is this? What is the f value here? Now in the question, I tell you, hey, look, the linear regression, the f statistic it gave back for this model was 5. Okay, was 5. All right. So where does 5 fall in here? We're not going to know until we get what the critical region here, the line, the demarcation line, the demarcation f value that separates the critical region from the non-critical region, or the region from where we reject the null hypothesis or we fail to reject the null hypothesis. Okay, let me write here, by the way, fail to reject null hypothesis. Oops. Yeah. And let me just copy this right here. Jeez. And here we simply reject the null hypothesis, and this will be this region right here. This region, this side, where we reject the null hypothesis. All right? So what is this f value right here? What is the f value that's going to give me this line, where this line exists? Now I come here. Now listen, during the exam, you're going to use an f table, right? An f table. For the purposes of R, I'm going to give you a function, right? The function we use is qf. All right? The qf, unlike qt, takes 3 parameters. Again, what level of confidence do we want? 95%, 99%? Do I tell you in the question? All right, I don't tell you in the question. So if I don't tell you in the question, always assume 95%. That always tends to be the default. All right, so 0.95, 9% confidence. Okay? Now, remember, the f-test takes 2 sets of degrees of freedom. Not 1, but 2. The first degrees of freedom is what? The first degrees of freedom is, that's right. The first one is going to be, sorry, back here. The first degrees of freedom we put in is basically the number of independent variables we have. I'm sorry, the number of independent variables we have, right? So in this case, if I slide over here, I have, and again, I'm sorry for the typo here. I have actually 1, 2 independent variables. I have 1, 2 independent variables. So here, I put in 2. All right, that's my, there are two sets of degrees of freedom, the df1. The first degree of freedom is always the smaller one. The second one's the larger one. And in the larger one, what's the larger one? The larger one is the same as the degrees of freedom from the t-test, right? It's basically the number of rows I have minus, I mean the formula at least, minus the amount of independent variables I have, minus 1 for my intercept. So in this case, it'd be 200 rows, minus 2 for those 2 independent variables, and then minus 1 for the intercept. And now I'll have my second set of degrees of freedom is 197. All right. And again, in the f-test, you literally have a table, and you'll look for the confidence interval you want and the 2 degrees of freedom, and it gives you the f critical region. I type this in. What's my f critical region here, guys? It's 3.04. Copy this. Right. Place that value right here. And now we go back to our, so that's the f value. That is the f critical region. That f score separates the fail to reject null hypothesis region from the rejected null hypothesis region. All right? And what is my f statistic? Tis 5. Where does that place? Where is that going to be placed? Over here. So therefore, I will reject the null hypothesis that all the coefficients of this model are 0, thereby having no linear explanation or linear relationship to the dependent variable. So we reject the null hypothesis. All right? So that's the answer for number 17. All right? Now, using number 17, can we improve the Z model, right? Can we improve the model? Yeah, we can. What does that mean? Basically, the only coefficients in there, just like in our slides, right, like our lectures, that are basically have no linear relationship to the dependent variable, right? And this is where I say, I give you the hint here. Well, we already saw that the coefficient has a t-statistic of 5.7 and a p-value that's so small. That means it's way out there, right, in the critical region areas of a t-distribution. But here, again, I have a t-statistic that's 12.6. That it's very large, but ignore it for now. I mean, I should make that smaller. But it has a p-value of 0.68, 0.68. That's 68%. 68%, ladies and gentlemen, puts you where? 68% puts you in this huge area of the probabilities. Remember, the probabilities in these tails from this point onward and from that point onward, 2.5%, 2.5%. 68%, if you have a value at 68%, it's got to be somewhere over here. It's got to be somewhere over here, right? Okay. Therefore, it's not in the rejection regions, it's in the fail to reject the null hypothesis regions. So therefore, this value right here, the water coefficient, the sunlight coefficient, it has its coefficient value basically means it's the standard error for the coefficient was too large. Because the standard error for that coefficient was so large, the coefficient value itself could be driven just by random error, right? Could be driven just by random error. So therefore, the assumption that, hey, its true coefficient value is 0, we can't reject that because we don't have any data to say to not be skeptical about it. So therefore, we fail to reject that null hypothesis, right? And therefore, can we improve the model? Yeah, we're going to rerun that model, but basically we're going to drop the water coefficient. So then we would rerun that model and basically get, well, whatever the new model would say. But basically what we do is we would run the model with just the water independent, just the water as the independent value, right? That's basically it. We would drop, or we would just drop the sunlight coefficient from our regression model. Okay, number 19. Using question number 17, if the adjusted R square ratio was 0.05, what does that mean? Who remembers what the adjusted R square ratio says? What that means is that 5% of the variation in the almond data, in the almond pounds data, 5% of the variation can be explained by my water and sunlight data. Can be explained by the variation in my water and sunlight data. Is that good? No, that's not good. Because then where's the other 95% of the variation in my almond pound data coming from? It's coming from somewhere else, right? Which means, and that's a hint for us for statisticians, I got to be looking at other coefficients. I got to be looking for other coefficients, right? So here it means basically only 5% of the variation in my almond data can be explained by the I plus enter variation in my independent data. And there it is, right? That's simple. All right, number 20. Okay, now we can finally get to number 20. Ooh, we have 30 questions on that. All right, fine. So I give you about 10 questions on basic R stuff. Again, testing your data tables, just as a refresher for you guys. All right. So for number 20, I say, what is M3 sum of 3? What's going on here? Well, we have an M3 table here, so let me construct the M3 table. The M3 table is going to be basically a data table with the columns X, Y, and Z. All right, X is going to be 1, 2, 3, 4, 5. y is going to be sequence 2 to 10. 2, 4, 6, 8, 10. And it looks like z is going to be 7 to 3. 7, 6, 5, 4, 3. All right? Okay, now, from here, we have to basically say, okay, this is the M3 table. All the rows, comma, so I'm selecting all the rows. Sum 3. Now look, I didn't give a column name. I just gave the number 3. What does that mean? Well, M3 comma 3 would just give me the third column. See, I didn't give the name, but I can give the position of the column. So this column. So the sum of the third column is going to be what? It's going to be basically 25. So the answer is 25. Very simple. Number 21. What is the sum of M2 comma 2? All right, I already have this. Oh, this is a typo, by the way. This should be M3, and this should be M3. So I apologize for the typo because these are M3 tables. So M3, okay, so 21, what is the sum of M2 comma 2? Now go do inside the parentheses first. So M3 comma 2 is what? It's basically this column right here. So this is just going to give me a vector of these values right here, and the summation of these values is going to give me 30. So 21 is 30. Number 22. What's number 22? Number 22 is, what is the sum? Okay, now this gets a little tricky right here. Now inside here, I'm saying, let me grab that table so you guys can see it. All right. So inside here, I'm saying, okay, this again is a typo. The table M3 plus repeat 2 comma 5. What does this do? Repeat 2 comma 5 do? What does that do? That creates a vector of 5 of an array of a vector of size 5 with each value in it being 2. So it's going to be literally 2, 2, 2, 2, 2. That's what that vector is going to be. Now when you add a data table to a vector, I've never showed you guys this before, but when you add a data table to a vector, what do you get? Data table plus a vector, you get a data table. But how does the math happen? How does the math happen? The math happens like this. If I may steal this right here. And it's literally going to be go down column by column. This is going to be plus 2, 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 plus, oh, sorry, other way. Sorry. Plus 2. You guys get the gist of what's going on here. Boom! Right? So plus 2, plus 2, plus 2, plus 2. And then, so this table is going to be enhanced by all the 2s. It's going to be added to all these new values. And then you're just going to take the summation of that whole table. Now, this summation of the whole table will work because all the columns are numbers. If just one column wasn't numbers, if it was some sort of strings or alphanumeric values, then you would get an error. But because they're all numbers, boom, the summation of all these numbers gives us a number value, numeric value. So in this case, the answer will be, so I'm adding, let's see, 10, 10, 10. So I'm basically adding 30 to whatever the summation here is, 70. So my answer is going to come out to 100. My answer will come out to 100. Now, given this, I just have a little now trick question for you that some of you might be wondering yourselves. Let's say hypothetically I said instead, what is sum of, this is a hypothetical question, M3 plus what does this become? Now we're saying the vector 1, 2, 3 plus M3. How do we answer this? How will this be answered? Actually, I should actually copy this. All right, now what's going to happen? Well, some of you will correctly guess that, okay, no problem. We know R doesn't throw errors. We know R will repeat, unlike Python. So this will be 1 plus 1 plus 2 plus 3, plus 1, plus 2. And then here, you would say, we start over again, plus 1. That's not correct. And this is something you would never know unless somebody told you, right? Unless somebody told you, or you just tried out for yourself. Or like me, you saw it in an interview question. So this is one of those other trick interview questions again, those gotcha questions. So here, this actually, what happens is, this vector right here, the 1, 2, 3 vector, it keeps repeating. So it's plus 1, plus 2, plus 3, plus 1, plus 2, plus 3. And then it starts over. Plus 1, plus 2, plus 3, plus 1, plus 2, plus 3, plus 1, plus 2, plus 3. All right? So that's just a little trick. And just in case, I wanted you guys to know. All right? So that is the trick question for number 22. Number 23. Number 23. I'm going to grab this, and I'm going to show you what's going on. So here, guys, this is a great way to visualize what's going on. M3, I have a single comma here, so I have a filter basically on my rows, and I'm choosing a particular column. We always start with filters. Y less than 6. All right, cool. So I come here, and I look for all the rows where the value in Y is less than 6. Well, that's just going to be these two rows right here, 4 and 2. Those values are, for Y, those Y values are indeed less than 6. So we're filtering for those two rows. Then I come here and I say comma X. And so I'm selecting just the X column from those two rows. It's going to be these values right here. So basically, what is my answer going to be? It's basically going to give me a vector that is going to be 1, 2. All right? Easy peasy. Number 24. Sorry. Number 24, all right? What is number 24? Number 24 now is basically saying, what is the sum? All right, we're getting a little fancy over here. Getting a little fancy. No problem. Let me copy this again. Okay. What is the sum of, again, we have this inside the parentheses. Do the inside the parentheses stuff first. So what is the sum of this, the second column, which is this, plus the X column, which is that, all right? So let me rewrite that so you guys can see it clearly. Sum of the second column, all the rows of second column, which is basically going to be 2, 4, 6, 8, 10. Plus the X column, which is 1, 2, 3, 4, 5. Right? So this simplifies into the vector. 2 plus 1 is 3. Remember, vector plus a vector, position by position. 2 plus 1 is 3. 4 plus 2 is 6. 6 plus 3 is 9. 8 plus 4 is 12. 10 plus 5 is 15. All right. And then the summation of these numbers pretty much gives you 15, 15, 45. All right. 15 plus 15 plus 15, 45. Number 25. Ah, yes, 25. I like 25. 25 is great for strengthening your basics. All right. So I give you 3 vectors right here, and I ask you then, what is the sum? What is this? Basically, this computation of these vectors going to give you. All right. So let's start off with what is giants. All right. Giants is basically, make this bigger. So giants is going to be 2, 3, 4, 5. Easy. What is cowboys? Cowboys is just going to repeat 3 4 times. No problem there. This is bigger. All right. Now eagles, we got something going on here. All right, eagles, we got something going on here. So eagles, I'm going to rewrite here. I'm going to show you how I simplify this. So eagles, I made this actually too big here. Need some more space. All right, eagles is basically this. C6 colon Giants bracket Cowboys bracket 2 close a bracket, close a bracket, close a parentheses, okay? So when you're dealing with something like this in programming, not just R, but all kinds of programming, start with the inside point and go out. Start with the inside point and go out. All right, in this case, start with the most inside data container you could find and go from there. So here, Cowboys is the innermost data container I could find. Once you identify the innermost data container, find the opening bracket and the subsequent closing bracket. So here's the opening bracket. Here is the closing bracket. So Cowboys of 2 is what? I come over here, 1, 2. Cowboys of 2, the second value in Cowboys is 3. So I can rewrite this and simplify it now, replacing Cowboys of 2 with the subsequent value it returns, which is 3. Now my next inner data container is Giants. Here's the open bracket, here's the closed bracket. So 3 of Giants is what? 3 of Giants is 4. So this now, Giants of 3 can be replaced by 4. And now 6 colon 4, C of 6 colon 4 is what? It's basically just 6, 5, 4. So eagles ends up becoming 6, 5, 4. And now I can do, let me slide this part up right here so I have more space to work with. And now I can do the first problem, number 25. Number 25, what is 25? Let me rewrite this again and I'll simplify it. So 25 again is sum Giants times eagles parentheses. All right, I'm going to go inside out again, guys, inside out. So the innermost data container I find is eagles, Giants, and eagles, but the Giants is wrapped in a sum function. I'll go there. So there, Giants is basically what? It's a vector. Okay. It's just a sum of the vector Giants. And sum of the vector Giants is going to give me what? It's going to give me the value 2 plus 3 plus 4 plus 5, which is 14. All right. And now this becomes 14 times eagles, where eagles is a vector, 6, 5, 4. All right. Now here, within the sum, we have vector mathematics going on inside here. 14 times 6, the vector 6, 5, 4. Now a number times a vector, it gives you a vector, right? A number times a vector gives you a vector. So this now gives me a vector. That's going to be 14 times 6, which is 84, 70, 56, done. And the sum of these values gives me 210. Done. All right? And that's number 25. Number 26, let me just copy these guys down again. Number 26 is this, sum Giants, this stuff right here. So again, I'll minimize this and then I'll add it all up. All right? So here, this becomes sum Giants plus C eagles Cowboys giants, bracket 1, close bracket, parenthesis, parenthesis. Parenthesis. All right, good. All right, so now, again, I minimize this. Find the innermost data container. That's right here, giants, open bracket, close bracket, so 1 of giants. So 1 of giants is what? It's just 2. So I'm going to take that and I'm going to replace it with its corresponding value that it's giving me back, which is going to be 2. All right, now what's the innermost data container we have? Well, Eagles and Cowboys. We could choose either one. I'll do the Cowboys one. So Cowboys here, open bracket, close bracket 2. The second value of Cowboys, that's 3. So I'm going to go ahead and minimize this. All right, and now I'm going to take the innermost data container again, which is Eagles, and this basically comes out to 654. All right, so so the C function of 654 comma 3 gives me what? It gives me giants plus 6543, right? And now I have another vector of math situation, vector mathematics situation. Giants is going to be 2, 3, 4, 5. Hold on right there. Okay, now we have vector mathematics, guys. So I'm going to go ahead and do the vector mathematics. It's going to give me a vector that's going to be 2 plus 6, 8, 3 plus 5, 8, 4 plus 4, 8, and 5 plus 3, 8. And the sum of 8, 8, and 8 gives me 32. All right, and that's number 26. So they seem tricky at first, but when you break them down, they're pretty straightforward. All right, number 27. All right, we have a couple manipulation problems, and then we're done. I think that's it, 30 questions. So A is going to be 6, 5, 4, 3, 2, 1. And now here we're doing a situation where the right side is going to be 10 and 20. And the left side, I'm choosing the second and fourth position to override. All right. So here we're going to have 10 and 20. And over here, we're going to have these values. That's basically going to be set equal to that. All right, set equal to these values. Now, the first value is the second value. The first value that's being overwritten is the 5 because it's in the second position. So that's going to be now give us the value. Let me just take this. So here, 5 will be overwritten to be 10. 4 will be overwritten to be 20. I'm sorry. The fourth value, which is 3, will be overwritten to be 20. And that's A. Now we do number 28. All right. What is A again? What A is 6, 5, 4, 3, 2, 1. I'll just take that. And here, this time, our right side is basically repeating 2 3 times. So that's basically this value right here. And on the left side, it's going to be this equal to those values, but in these particular positions. All right. The second position, which is 5, will become 2. The third position, which is 4, will become 2. The fourth position, which is 3, becomes 2. And so this is what A ends up being right here. Number 29. What is mm? mm's a doozy. Mm is 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. And now we are saying, okay, make the right value, which is 12 and 13, set these values, 12 and 13, equal to the second, 3, and 4th position of mm. All right. So what is the second value of mm? The second value of mm is 2. So that 2 now becomes 12. All right. What is the third value of mm? The third position. What is the third position of mm? That is 3. That 3 now becomes 13. Okay. And now what is the fourth position of mm? The fourth position of mm is 4. But I have no more values here. So what ends up happening? In Python you get an error, but R, what does R do? R just starts repeating the values. So now we go back to 12. So my fourth value now becomes 12. My fourth value now becomes 12. And that's what mm becomes. All right? And similarly, number 30. 30 is a flip side of that example. So I have this mm again that's here. And on the right side, I have equals a vector from 100 to 1. So I'm not going to write all that out because that's a lot. So it's literally going to be 100, 99, 98, 97, dot, 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 hold on, comma, dot, 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 comma, 1, 2, comma 1. All right. The name you entered is not valid. Yet that's fine. Oh, sorry. Let me get rid of that. Get rid of that equals so it doesn't mess it up. All right. So that is going to be a vector from 100 or going all the way to 1. Okay. Here now. Okay. Here now, let's change up those values, shall we? So the second position, the second value in mm is going to be overwritten. Oh, I'm sorry. I'm looking at the wrong one. Number 30. So here, the seventh, notice what's here first, guys. The seventh, first of all, hold on. I did this wrong. Apologies. I'm looking at the wrong problem. It should be 9, 8, 7, 6, 5, 4, 3, 2, 1. Sorry about that. Some of you guys are probably screaming into the YouTube screen right now. All right, there. Now it's fixed. All right, now let's get started. All right. So look what's happening here. It's the first value that's being overwritten is what? Is the 7th position. What is the 7th position? 1, 2, 3, 4, 5, 6, 7. It is 3. It is 3. 3 will get the first value in the array on the right side of the equals. So 3 gets overwritten to be 100. Okay? Now the second value that's being overwritten is 3. Where the third is not 3, it's the third position. The third position of mm. 9, 8, 7, 1, 2, 3. This is the third position. The third position is being overwritten to be now the next number up, which is 99. Okay? And now the second position in mm is the next one up to be overwritten, and that's the 8. And the 8 now finally gets the value 98. And now that's it. There's no more values to be updated to the left of the v equals, right? There were just 3 values. So all these other numbers now, that's it. They're out of luck. No go. It's done. And number 30, mm, ends with this value. 9, 98, 99, 654, 100, 2, and 1. Okay? And this concludes practice set 4 solution. I look forward to check it out. Do it. And I'll see you guys at the next Q&A session. All right? Have a good day, guys.